So we have another method of integration called integrating rational fraction. So let's first define what a rational fraction is. So a rational fraction is a quotient of two polynomials. So if you have the polynomials n of x and d of x, where the two are polynomials with real coefficients and have no common factor other than 1. So we have the numerator and the denominator. So it's a ratio of two polynomials. So an example is this one. So this is a ratio of two polynomials where the degree of the numerator is 2 and degree of the denominator is 3. So the degree of the numerator is less than the degree of the denominator. So the rational fraction is a proper, okay, rational fraction. So just like in simple fractions, if the numerator has a lesser value compared to the denominator, for example, one third, so it's called a rational, no? Or meaning it's called a proper fraction. So if it's otherwise, then the fraction is said to be an improper fraction. For example, 4 over 3. Okay, 4 is greater than 3. So it's an improper fraction. So if we have n of x and d of x, so it's again an improper, okay, rational fraction. So we have here an example. Okay, so the degree of the numerator here is 3, and the degree of the denominator is also 3. So if either the degree is greater than or equal to, okay, the degree of the numerator is greater than or equal to the degree of the denominator, then it's an improper rational fraction. So another example is this one, wherein the degree of the numerator is 4 and the degree of the denominator is 2. So 4 is greater than 2. So this is an improper rational fraction. So in algebra, usually we combine two or more fractions to form a single fraction. But here, since we are already going to integrate no, the fraction, so if ever the integration methods, simple substitution, for instance, cannot be used for rational fractions, then we need to divide the fraction into simpler fractions so that we can already apply the different formulas in integration. So we need to resolve a single fraction no, into what we call partial fraction. So here's an example. So if we have this proper fraction, it's a proper fraction because the degree of the numerator is 2 and the degree of the denominator is 3 because we have three linear expressions here. If we multiply these three, the result would be an x cubed for the first term. So it's of degree 3. So 2 is less than 3. So this is a proper fraction. So we can resolve this single fraction into these three simpler fractions. So these are what we call partial fractions. If you're going to add these three, the result would be this single fraction. So for improper rational fractions, so since it's improper, the degree of the numerator is greater than the degree of the denominator or equal. Okay, the degrees are equal. We need to express it as a quotient no, plus a remainder. So for example, if we have 4 over 3, it's an improper simple no, fraction. So we need to divide no, 4 by 3. So we get 1 and 1/3, right? So we have a whole number and a fraction. So we can already apply the different formulas in integration. So once we have already a bale, an expression no, that is not a fraction. And for the fraction part, so if there is a need to resolve it into partial fractions, then we need to resolve it into partial fractions. Or if we can already use substitution, a simple substitution method in integrating no, the fraction, then of course no, that would be the best option. So for example, if we have the single fraction, okay, so we have x cubed over x squared minus 4. So it's an improper fraction because the degree of the numerator is greater than the degree of the denominator. Okay, so 3 is greater than 2. So we need to divide this by long division. Okay, so please do not just cancel out x squared because it's not a common factor no, for the numerator and denominator. Okay, take note there's a difference of two terms here. So meaning the entire numerator must be divided by x squared minus 4 and not divide it by each term here no, in the denominator. Okay, that's wrong. No, so we need to use long division to get the quotient no, and the remainder. So you need to write first the numerator. Okay, if ever there are missing terms like the x squared, x, and the constant terms, so you can just um, write no the terms with zero for the coefficients so that you will not forget no that there are missing terms. Okay, or it's not necessary, no? So if you already know how to do long division, then writing these missing terms, okay, is not required. So for the divisor, put it here. So in long division, recall no that we need to arrange the terms accordingly. It should be in decreasing order of exponents. So first is divide the first term by this first term here in the divisor. So x cubed divided by x squared. So that's x. And then multiply x to each of the terms in the divisor. No, so x times x squared, that's x cubed. X times 4, that's negative. That's x times negative 4 rather. So negative 4x. So the x term is on this column here. So you need to write the minus 4x here. And then perform subtraction. So x cubed minus x cubed, that's 0. And then 0x minus negative 4x, that's 4x. So if the degree of the remainder here is already less than the degree of the divisor, then you need to stop with the long division. So meaning this is the quotient and the remainder is 4x. So this single fraction is equal to x, okay, over, or rather, this is the quote unquote whole number, and the fraction is 4x, okay, over the divisor. So the remainder over the divisor. So if we're going to integrate, okay, this, there's already a formula no, for this using power rule. And for 4x over x squared minus 4, you can let u be equal to x squared minus 4 and du be equal to 2x dx. So there's an x here. So meaning, okay, the numerator no, will form the du. So you can integrate it by using simple substitution. So that's the introduction no, for partial fractions.